By the end of this video, you should be familiar with all the pros and cons of using UniTask over coroutines, tasks, and even the new Awaitable class, and how to replace your usage of those things with the UniTask library. In a nutshell, UniTask is a framework that can handle those kinds of operations with zero memory allocations. So we're going to quickly go through coroutines and tasks and discuss how they allocate memory, and then we'll get right into how you can use UniTask to consolidate your async workflow and in most cases, completely replace these other methods. We're also going to take a look at some of the more advanced features that the library offers and compare UniTask to Unity's new Awaitable class, which came out in version 2023.1. So let's get started. I've set up a pretty simple scene here that has 3 different progress bars. The red bar we're going to connect to a coroutine, the blue bar we're going to connect to a traditional async task workflow, and the green bar is going to be exclusively UniTask. We're going to look at methods later in the video on how we're going to convert the red and the blue into UniTasks, and this will give you an idea of how easy it is to start using UniTask in your own project without changing a lot of your existing code. I'll leave a link to this progress bar asset in the description. Let's start by creating an example coroutine. So returns IEnumerator, it's going to accept a progress bar. All I really want to do is fill the progress bar up from 0 to 100%. So every 50 milliseconds, we're going to increase it by 1 more percent. That's it, very simple. Let's start the coroutine running inside of the start method on progress bar number 3, which is the red one. I'm also going to add an awake method here just because I want all the progress bars to start exactly at 0% and not the default value I have there in the scene. So with that all done, I can collapse up this awake method and let's jump back into Unity, just have a sanity check, make sure that everything is working as expected. So I hit play and of course we see the progress bar going from 0 all the way up to 100, no surprises there. So let's go talk about the pros and cons of coroutines. Start coroutine, stop coroutine, and related methods are part of the MonoBehaviour class. So a coroutine is directly tied to the MonoBehaviour that started it. That means coroutines automatically stop when the game object is destroyed or disabled, but keep in mind that coroutines don't automatically resume if you re-enable a game object. Coroutines return an instance of IEnumerator, which Unity's runtime uses to run and manage the coroutine. Under the hood, this is creating a small state machine class. So while the runtime is making you a small state machine here, it also means that you can't return a value from a coroutine, at least not directly. You could pass in a callback method or find some other way. So usually when you start up a coroutine, there'll be a small amount of heap allocation, and that's just to create that little state machine object and get it started. What has a much bigger impact on your game is yield instructions and behavior inside of the coroutine. You can see here that I'm repeatedly creating a new wait for seconds object. Let's take a closer look at it. I'm going to quickly switch back to Rider's classic UI using this plugin. Now, in this wait for seconds class, all I wanted to point out in here is that wait for seconds inherits from yield instruction, and it is in fact a class. So every time you make a new wait for seconds, you are making a heap allocation. Now, this is a problem we addressed in an earlier video where we created a system for caching instances of wait for seconds so that we could retrieve them without having to create a new one every single time. That's available in the Unity utility library. There'll be a link for that in the description. Now, if you aren't satisfied with the basic yield instructions that are available to you, you can also make custom yield instructions. So this is another nice feature of coroutines, or really any enumerator. You can create a custom yield instruction. All you have to do is override keep waiting and return true or false based on some condition, whatever you want. Okay, let's clean this up just a little bit. A very common mistake in Unity coroutines is doing a yield return 0. You can see if I mouse over here, it says boxing allocation because we're converting an integer into an object. This exact code was the cause of a big bug in Unity about 8 years ago. And you're likely to see this in all kinds of examples on the Unity forums. The proper way to skip one frame in a coroutine is to yield return null, and there's 0 allocations. Now, yield instructions aren't the only way that you can allocate memory inside of a coroutine. Of course, most heap allocations are obvious because you're going to see the new keyword. You're going to know that you're instancing a new object. But one that gets past a lot of people, especially beginners, is closures. So let's suppose we have an integer, which is a value type, some value equals 5. If I yield return a new wait until, first of all, I've got a new yield instruction here, but the yield instruction contains a closure. Now you can see from the pop-up hint here that not only are we making a delegate allocation here, but we are also capturing that value, some value. Some value is no longer just this value type that exists within the coroutine. We now have to keep it and reference it inside of the wait until yield instruction. So wherever you have a lambda that captures variables from the surrounding scope, you now have created a closure. And a closure is going to have a small amount of heap allocation. All right, let's talk about one more limitation of coroutines, and that is if I were to wrap this entire thing inside of a try catch, well, watch what happens. You can see I can finish the try, but when I go to put my catch instruction in here, I'm going to get a nice red squiggly line under my yield return statement. And why is that? Well, yield return statements cannot appear inside of try catch blocks, and that's the expected behavior. Another thing that a lot of people don't realize is that you can actually run other MonoBehaviour methods as coroutines. So for example, the start method doesn't have to return void. Start can return an IE numerator, but that does mean that we need to have a yield statement inside of the start method. So that means, for example, you could wait for one frame or you could wait for some process to run inside of your start method before you continued executing the rest of the logic. Okay, that's enough coroutines. Let's move on to async await. The rest of the video is going to be entirely asynchronous programming, so let's change the signature of our start method to be an async void. Now, before we get into UniTask, we're going to do some vanilla async await just to talk about some of the concepts and talk about garbage collection. Avoiding heap allocations is the number one reason that people would choose to use UniTask in their game, but it's really not that much different than an async await workflow. Let's make a little asynchronous method here, perform calculations async. So it's going to return a task of type int. We can simulate a long-running operation here by awaiting the task.delay method, let's say 100 milliseconds. And then after that, let's just return some little operation. So we can take the input, multiply by 2, and return that. In our asynchronous start method, let's just await that method to complete, and we can output the result. So let's talk about the allocations involved in this simple operation. When we await the perform calculations async method, under the hood, just like with coroutines, a little state machine object has to be created that's going to maintain the state of that operation. And this is the number one thing that turns people off from using async methods in their Unity workflows. There's going to be a lot of awaits. That means a lot of allocations. Furthermore, anytime you create a new task, that's creating a new task object. That's not really any different than the wait for seconds. So when you call task delay, you're getting back a task object. And also when you return input multiplied by 2, it's going to put it into the task of type int. So that's a lot of allocations in a tiny method that does almost nothing. The way things are running right now, the perform calculations async method is still running on the main thread. Let's suppose we wanted to run something on a different thread. We could make another method here, expensive calculation. All I'm going to do is just add up all the numbers from 0 to 100 million and return the result. To get a thread from the thread pool, we have to actually use the task.run method. So I'll comment out the earlier method. We will now await task.run, and we will send in the expensive calculation to be run on some available thread. Well, maybe we can actually demonstrate that really quickly. Why don't we output the main thread ID, and I'll turn this lambda into a statement lambda, and we can add a debug statement here as well, saying that the expensive calculation is running on thread ID, and we'll output the ID in the context of this task.run method. So if I hit play, we'll see that the main thread ID is 1, of course, and the expensive calculation is running on thread 2469. If I run it again, of course, it's going to choose a different thread, so it gets 2352. And so that's task.run in a nutshell. We're not going to dwell on this, of course, because if you really wanted to do multi-threaded operations in Unity, you should really consider the job system. Let's get back to async await. Let's clean up this multi-threaded code because we don't need it anymore and collapse up this expensive calculation method. It's worth pointing out that you don't have to return a task of type int here because we're returning a value. We can use the struct type value task instead. That'll save us one allocation. Keep that in mind when you're doing these kinds of things. UniTask will completely replace task and value task. We're going to look at that in a minute, but I want to clear up one more thing before we do that, and that is cancellation of asynchronous operations. Very important to understand before you get into UniTask. Unlike coroutines, we don't really stop asynchronous operations. Instead, we cancel them. A cancellation token source is a class that produces cancellation tokens, and it can signal cancellations to any operations that are using the tokens it produces. In a way, it operates just like an observer class. The token itself is a struct that we use to signal that an operation should be canceled. So to demonstrate how this works, let's scroll down a little bit. I'm going to create a new method that will accept a cancellation token, and we'll use it as an example. Inside the method, let's just make a loop that iterates 10 times, has a little debug statement to say which step we're on, and then it'll wait for 1 second. Now to handle the cancellation, we just have to add one more line here. Token.throwIfCancellationRequested. What that'll do is throw an exception that signals the cancellation of this asynchronous operation. Now, usually when we throw an exception, that's because something went wrong in our code. But this method was designed to work with the cancellation framework in .NET, and it indicates that a task was canceled intentionally. So let's start our task running with a new line in the start method. We'll say task equals some long running operation async, and we'll pass in the token. Now, it's a common misconception when you're dealing with async await and tasks that you have to actually call the await method to start a task running. This isn't the case. As soon as you've initialized the task, it begins running. So let's introduce a little delay for 3 seconds, and then we're going to cancel all of the tokens that the token source has created. Now let's check on the status of our task. In a try-catch block, we can await the task, and we can catch an operation canceled exception. Maybe for a sanity check at the end of our some long-running operation async method, let's say if we actually finish the task or not. Okay, I think we all know what's going to happen, but let's jump into Unity and just make sure we have a good understanding of this by running it at least one time. So I'll press play. We should see 3 steps execute. After 3 seconds, our cancellation fires, and that's it. So leading into our UniTask examples, let's make a version of our coroutine from before that was moving the progress bar, but this time we'll use an async await workflow. And for this one, we'll pass in a cancellation token. It'll be very similar to the method that we just wrote. We'll just increase the progress bar by 1% every 50 milliseconds. Then up in our start method, let's get rid of the example from before. All we're going to do is await this method. So hit play, and yes, of course, we see the middle bar, the blue one, starting to fill up. Now let's start implementing UniTask. UniTask is an open source project, so we can go and grab everything we need from GitHub. On the GitHub README, you'll find the URL you can use to import the package into your project. Just drop in the URL there, click install. It just takes a few seconds, and then you're ready to go. Then all you need to do is come back to your code and add one using statement, sci#.threading.tasks. Now, to show how simple it is to convert an asynchronous workflow into using UniTask, I'm going to copy the asynchronous method we just wrote. I'm going to paste it above and give it a new name. Now, this is actually very simple. Instead of returning a task, we are now going to return a UniTask. Unlike a task, a UniTask is a struct, which means it has 0 heap allocations. Similarly, UniTask.delay is optimized for Unity, providing a lightweight 0 allocation delay that integrates seamlessly with Unity's player loop. Now, UniTask.delay and UniTask.delayFrames have multiple optional parameters that you can pass in, so that's why I'm using a named param for the cancellation token here. So just by making those 2 changes, we can now come up to the start method and await this example UniTask, and we'll have a 0 allocation asynchronous operation. Let's go try it out. Before I hit play, I want to show you one of the more impressive features of UniTask, and that is the UniTask tracker. I've got mine docked up here right by the inspector so I can see what's going on. Why don't we press play and see what happens? So first of all, we can see the bar is filling up. But if you look up in the UniTask tracker, you can see there are actually 2 UniTasks running. One is us awaiting the actual progress bar filling, and the other one is the UniTask delay. Now, of course, when they're done running, they don't show in the tracker anymore. Let me just grab a clip from a little bit earlier and blow it up. So you can see we have some useful information here, but even more useful than this is to enable the stack trace. If you've got a task that runs away and it just keeps running after you exit play mode, you're going to be able to find out exactly where it came from so that you can deal with it. Remember that tasks don't automatically stop just because a game object is destroyed or that you come out of play mode. It's in memory and it's a running asynchronous operation. So either it's going to stop running because it was finished what it was supposed to do, or you have to cancel it yourself. So while we're on that subject, why don't we start running multiple asynchronous operations at the same time and look at ways that we can actually stop them. So I'm going to make a using block here, and I'm going to define a new cancellation token source to use within the block. One of the best features of UniTask is that you can use it to control all of your coroutines, all of your methods that return UniTask, or even any of your methods that return task. Now we've got 3 example methods here, one for each of the progress bars. What I'm going to do is await a new UniTask.whenAll method. That means it's going to wait until all of the operations we pass in have completed, or they get canceled. The first one is simple. Call the method, passing in progress bar 1, and the cancellation token. For our method that returns a task, it's very similar, except we're going to use the extension method as UniTask. That'll convert the task that gets returned into a UniTask. For the coroutine, we're going to call the method, but then we're going to use the extension method with cancellation and pass in the token that way. With cancellation actually returns a UniTask. It's a simpler version of the method to UniTask, which takes more parameters. Now, maybe just for completeness, down at the bottom, let's add a debug statement that tells us when we've actually finished all of our tasks. And let's make sure that I'm passing in progress bar 3 to the coroutine. And you know what? I'm going to keep the shorthand form of this to UniTask. Let's keep it as with cancellation. So now when I hit play, all 3 bars should start running. We should see a lot of tasks up in the tracker. And when they're finished filling up at 100%, we should get a message in the console. Yep. Perfect. But what if I wanted to stop these a little bit early? Let's say that we change the first progress bar to finish at 50%, and then we change our method from being a when all method to be a when any. That means when any of these tasks complete, we will finish waiting. And as soon as one of them is finished, let's run the cancel method on the cancellation token source. That should stop the other 2 jobs, even the coroutine. So I'll just hit play, and I expect it just to run to 50% on the first bar, and that'll halt everything. Perfect. All the bars stopped exactly at 50%. There's a few other ways to handle cancellation with UniTask. Let's remove this using block, and instead, one way you can handle this is UniTask provides an extension method to the MonoBehaviour class, which is GetCancellationTokenOnDestroy. Using this token synchronizes your jobs with the lifecycle of this game object. So everywhere before where I was calling the cts.token, we can just replace that with this token, and we'd be assured that as soon as this game object is destroyed, our jobs stop running too. Now, you might want more fine-grained control over the cancellation of your jobs. What I would do is declare a cancellation token source at the class level, and that way you can cancel it anytime you want, including in onDestroy, or really anywhere else you might need to. You can also fire and forget any UniTask by using the forget extension method. So that's useful when you want to suppress any errors or warnings and you don't want to wait for the return type. And if you don't care about the return type, you can return a UniTaskVoid instead of a UniTask. That's the UniTask equivalent of Async Void. Of course, that's not going to work inside of our when any method, but if you were going to do a fire and forget on a single task, it's the recommended approach. But maybe you don't like this asynchronous workflow at all, and you just prefer to work with the coroutine system. Another thing that you can do is use the toCoroutine method and convert any UniTask into a coroutine, or more specifically, into an IEnumerator. Then you can start it like a coroutine, or you can yield return it like a coroutine. Of course, there are many more extension methods that you can use with UniTask, and they're all just about as simple as this. And actually, if you've grasped everything that we've talked about in the last 5 minutes, that's really the bulk of it. However, there are a lot of really advanced features in UniTask as well that I won't be able to cover all of them in this video, but I'd like to take a look at one of them, and that is Asynchronous LINQ. You can see up at the top here, I've added one more using statement, and that's for the UniTask helpers related to LINQ. So we're going to make a very simple asynchronous LINQ operation. Let's wrap it up in its own method. We'll call it run async LINQ example. We'll pass it in a cancellation token, same as we would do for any async operation. Now we're going to use the UniTask async enumerable class to actually create an async enumerable. For this example, we're going to generate and process a stream of frame updates. So we're going to grab data during the update part of the player loop. We're only going to grab 10 of them. Now we can use select await to asynchronously process every element in the sequence. Inside of here, we're going to have a little 100 milli delay, and then we're going to return time.time. Now, while not strictly necessary in this example, you could filter out any duplicates that come in through the stream using distinct until changed. Finally, we're going to use a for each async. This will iterate over every element in the filtered sequence asynchronously and will log out the time value. Now, notice that we passed in the cancellation token the whole way through this journey, so that if we wanted to cancel this task, like for example, the game object gets destroyed, it'll stop the task too. Now, all we have to do is await this particular UniTask. When it's finished, let's log something out to the console. Up in the start method, we can actually execute this method as a fire and forget. So let's just use the forget extension method. And you know what? While we're at it, let's change the return type of our method from UniTask to UniTaskVoid, because I don't care about the return value. And in fact, we can make this entire thing quite a bit less verbose. If we use some C#8 syntax, we can use an await for each instead of that longer LINQ statement. This does the exact same thing, except I've removed the duplicate check. So I hope that makes sense. I know it's kind of a more advanced topic, and we're getting very close to what UniRx does. The difference is UniTask async enumerable is pull-based, where the data is requested by the consumer at our own pace, while UniRx is push-based, where data is pushed to the consumer as soon as it's available. So why don't we jump back into Unity and actually see what this is going to do. So of course, we're going to have 10 iterations here. And during the update section of the player loop, we're going to output what frame we're on and how much time has actually elapsed. So exactly what I expected. If you take a look at the documentation, there's actually a very interesting example of waiting for a certain number of button clicks, which is another simple but very good use of this kind of functionality. You might have also noticed that the second two bars ran all the way to completion that time, and that's because I didn't cancel the job. The whenAny method will complete when any of the tasks passed to it completes. However, this does not automatically complete the other tasks. There's just a few more things I want to point out during this video. The first one is that the UniTask struct is a generic type. So that means you can return a UniTask of any type T, for example, type int. A UniTask can also have the same behaviors as a coroutine in that you can delay for a certain number of frames, even a time span, or you can yield to a specific point in the player loop. For those of you that watched the video on this channel about the player loop, UniTask uses a lot of those same techniques to hook right into the player loop as its own system. Now, another nice feature about returning a specific type of UniTask is that unlike a coroutine, we're actually going to be able to do something with the return value of the method. If we were doing this in a whenAny or a whenAll, for example, if I call this new method that we just wrote, they both return integers. What we can do is deconstruct those as a tuple. So you can see how this can totally replace coroutines with a few more advantages, actually. And of course, the entire operation is extremely lightweight. Now, before we wrap things up, I do want to talk about Unity's new Awaitable class that came out in 2023.1. This class has one big pro over UniTask, and that is that it's built into the engine. You don't have to rely on a third-party library. Just like the UniTask object, an Awaitable is a replacement for the task object. The Awaitable class has all kinds of nice helper methods that let you wait for frames or for seconds. You can assign an Awaitable into a variable, and then you can await that variable to complete. Awaitables have a public method cancel, which does the exact same operation that we were doing earlier with tokens, but it does mean that you have to have a reference to the awaitable. Otherwise, you can cancel awaitables using tokens the same way we've been doing for tasks and for UniTasks. You can also use a generic awaitable the same way we're using a generic UniTask. So if you need to pass a value back from an awaitable, you certainly can. Both Awaitable and UniTask have their own version of a completion source. Now, these are versions of a task completion source, which allows you to turn any callback or method into an asynchronous operation. So they both have their own versions of this. And this is a feature that I'm not going to get into. It's very easy to understand. You can look it up in the documentation if you wanted to do something like that. And so in a lot of ways, Awaitable and UniTask are comparable. The biggest difference is that Awaitable is a class, UniTask is a struct. And the way that awaitables work under the hood is that they just get pooled up in the system. And when you request one, you're getting one out of the object pool. So while it's not totally allocation free, it is managed pretty nicely. And if you don't abuse it, you probably won't see too many allocations at runtime. Both UniTask and Awaitable have one restriction, and that is you cannot await a UniTask or an Awaitable more than one time. If you do it with an Awaitable, you're going to get a null reference exception because it's gone back to the object pool. If you do it on a UniTask, the behavior is undefined and it may or may not work. Okay, well, that was a lot going on in one video. If you have any questions at all about UniTask, about asynchronous operations in Unity, or if you're interested in seeing a video about UniRx, please leave a comment below. If you're considering bringing UniTask into a project, it's definitely worth going over to the GitHub page and having a full read of all of the documentation in the README. There's a lot of extra features and extension methods that I just can't cover in one video. We're going to be talking a lot more about asynchronous operations in Unity in the future, so if that sounds interesting to you, hit the subscribe button, hit the like button, and don't forget there's a link to our Discord channel and all of the assets that you saw in today's video in the description. If you're interested in watching more videos from the channel, I'll put something up on the screen. Maybe I'll see you there.